Dear students, this is our third lecture on stereochemistry, and in this lecture we will discuss details about CRAM'S chelation model, or this is also called CRAM'S cyclic model. In the previous lectures we have discussed the CRAM'S rule first, and as you know, the CRAM rule is basically for ketones which are acyclic in nature. But in the details about CRAM'S rule, we have seen that CRAM'S rule has some limitations and some aspects which cannot be explained. And those limitations or drawbacks, they were come over by the second rule, which is called as Falcon's rule. And in the second lecture on Falcon's rules, we have discussed about the overcome of limitations of CRAM'S rules, in addition to some modifications of CRAM'S rule, like Falkenhayn rule also. And some of the product formation is not explained on the basis of CRAM'S rule or Falcon rule, and those are explained on the basis of a cyclic model, which was also proposed by CRAM in 1959, whereas the acyclic model was proposed by CRAM in 1952. So that was only cyclic model was only given because of the formation of products with different selectivity, and it was found by CRAM that this different selectivity product formation is because of the chelation which is present in these types of compounds. So what CRAM found that was that if there are alpha hydroxy or alpha amino ketones, then the application of acyclic model or cyclic model will predict different outcomes for these systems. That means different products, they are possible if we choose a cyclic model or an acyclic model when we are having the carbonyl systems where we are having alpha hydroxy or alpha amino ketones present. Now, out of the cyclic and acyclic model, it was found that cyclic model is applicable only when there is a chelating heteroatom present on the alpha carbon. So, for example, in this molecule, Z is the chelating heteroatom which is present at the alpha carbon of the carbonyl system. And furthermore, this alpha carbon should be a stereocenter also. And when such type of compounds, they reacted in presence of metal systems, then they will form a cyclic chelated complex, which will lead to the formation of products with different selectivity. So in such cases, what happens is that a chelation of the metal complex occurs with the oxygen of the carbonyl system and the hetero atom which is present at the alpha carbon, and this hetero atom is generally oxygen or sulfur or nitrogen which is having a lone pair, one or more lone pairs present on it, and these lone pairs, they are capable of coordination with the metal, and this will lead to the formation of a cyclic chelated complex. and in such cases the nucleophile will attack from the least hindered side of the molecule to give us a product with anti-Falcon selectivity. And cyclic model will mainly applied for alpha alkoxy carbonyls, which where the formation of the complex will be through a five-membered chelate. Similarly, if we are having beta alkoxy carbonyls, then the six-membered chelate will be formed, but the product formation has been found to be less selective in comparison to alpha alkoxy carbonyls. But when we are using cuprates, then beta alkoxyaldehydes, they give us the selective products also. Now, some points about this chelation model is that here the alpha substituents, as I have told you, oxygen or sulfur or nitrogen. So they are having lone pairs, and these lone pairs they can coordinate with the metal ions, and metal ions they can be divalent or higher valency metal ions, and the coordination will be with the metal ion and the oxygen of the carbonyl. Then the chelation ring becomes the dominant factor in determining the conformation. So there will be a specific conformation which will be more favorable, that will be formed due to this chelation ring, and because of that this will give a very high selectivity for the attack of the nucleophile from the side which is least hindered. The most common chelating metals are zinc, copper, titanium, cerium, magnesium, and non-chelating metals, they are lithium, sodium, and potassium. And as I have told you, because of the formation of a specific transition state, we will get products with a specific diastereoselectivity, and in case of cyclic chelation model, the products they are formed with anti-Falcon selectivity. If there will be a formation of a chelating complex, then the product formed with will be with anti-Falcon selectivity. Now, for example, if we consider this organometallic addition reaction of methyl titanium trichloride with 2-benzyl oxypentane 3-one, and here we are having this heteroatom part as the chelating part along with this oxygen of the carbonyl system, and we can see here a CRAM chelate is formed with methyl titanium chloride, and here the nucleophile is our methyl, and this will attack the carbonyl from the least hindered side, leading to the formation of the major product with anti-Falcon selectivity. So this is how the product formation in such type of cyclic chelating complexes is formed. Now, different types of effects they are observed in the cyclic model in the formation of diastereoselective products. That effect may be due to temperature, that effect may be due to nucleophile, that effect may be due to type of Lewis acid which is used, that effect may be due to the steric hindrance which is present in the molecule. So we will discuss these effects one by one. First is effect of the nucleophile. Now if you see these two reagents. One is lithium aluminum hydride, other is zinc borohydride. Here the nucleophile which is generated from both of these. So here hydride ion will be the nucleophile, and here BH3 will be the nucleophile which will attack the carbonyl system. Now the type of reaction which is taking place is reduction, and we are using only this one reactant for both of these reactions under same conditions. So when reduction of this 1s 1 hydroxy 1 phenyl propane 2-one is done with these two nucleophile, it has been observed that both of these they undergo chelation. So when we are using lithium aluminum hydride, here the aluminium metal will be the chelating metal, whereas when we are using zinc borohydride, then chelating metal will be the zinc, and the nucleophile is attached to zinc and it has to attack from the least hindered side. Now the depending upon the coordination strength of the nucleophile with the metal, this will be released from the metal complex to attack the carbonyl, and because of that, the as the type of nucleophile is different, it has been found when lithium aluminum hydride is used, then product with antifalcon selectivity, that is the major product, is formed in 60% diastereoselectivity. Whereas similarly, when instead of lithium aluminum hydride we use zinc borohydride, then the diastereoselectivity increases to 80%. So you can see yourself that the type of nucleophile do affect the type of product formation, or the type of diastereomer formed in these types of reactions. Similarly, effect of steric hindrance. If we see these two substrates, here the heteroatom present is methyl ether, and here the heteroatom present is tertiary butyl diphenyl slide ether, right? And if we see the steric aspects of both of these substituents, this is sterically much more hindered in comparison to methyl ether. Rest of the molecule is same, right? Now if we see this, only difference is this and this in the molecule, and if the reaction is performed under same conditions, we treat these with dimethyl magnesium at minus 78 degrees centigrade. That means the type of chelating agent and the nucleophile used is same, the temperature is same, so we are doing the reaction in same conditions. This reactant undergoes chelation to give us this type of favorable transition state, and this gives us this type of favorable transition state. Both the transition states, they are formed by chelation, right? So that means mechanism of both these reactions is same. Now here only difference is the steric hindrance on the heteroatom molecule present, and we can see that product with antifalcon selectivity formed in this reaction is with 99% diastereoselectivity, whereas here the product formed with antifalcon selectivity is only 30%. So here this is some mistake. Here instead of O-methyl, it should be tertiary butyl diphenyl silane. So there is a mistake. We have to replace this methoxy by this group. So here the product formed with anti-Falcon selectivity will be only 30% diastereoselectivity, selectivity, whereas here this is 99% diastereoselectivity. selectivity. Now similarly, effect of solvent can also be seen along with the effect of this protecting group. Now say we are having this reactant where the heteroatom is this one ether group, and this R is different in two places. At one reactant, R is tertiary butyl diphenyl solid ether, and other is benzyl oxymethyl ether, which is used as the protecting agent. Now, when this reaction is done with lithium aluminum hydride at minus 10 degrees centigrade, uh, when we are having this R as benzyl oxymethyl, and we are using either tetrahydrofurane as solvent or diethyl ether as solvent, you can see that when these solvents are used in presence of this R as CH2OBN, that is benzyl oxymethyl, you can see the transition state involved is this one through chelation model. Then when we are using THF for diethyl ether, under these circumstances, when this R is benzyl oxymethyl, then this will be the transition state and this will be the major product formed. That is, product with anti-Falcon selectivity will be formed in 70% when THF is used, and if instead of THF we replace that solvent by diethyl ether, then product with anti-Falcon selectivity formed will be 98%. So we can see that effect of the solvent on these reactions, with the change of solvent, the stereoselectivity has increased to that much extent. Now similarly, effect of if protecting group is to be studied. Now here this is the protecting group with THF, whereas here this is the protecting group with THF, that is tertiary butyl diphenyl silyl is used as the protecting group, but solvent is same, temperature is same, reagent is same, rest of the conditions are same, only difference is this R in this or this. We can see that here the model involved will be a chelation model, whereas here the model involved will be polar Falkenhayn model. Here there will be no chelation for the formation of the product, and here we will find that the product is formed with Falkenhayn selectivity with 95% diastereoselectivity. So these two examples will clearly tell the effect of solvent and the protecting group on different types of carbonyl systems. Similarly, Lewis acid also affects the formation of different types of products in this chelation process. If we are having say this type of carbonyl system which is involved in product formation, and we are using different types of Lewis acids, and solvents under different conditions, then the type of products formed, they are also different. Now, for example, in this molecule, only difference is this protecting group, and is this protecting group is benzyl oxymethyl or tertiary dimethyl silane. Now, if we compare, say, with the same protecting group, you can see these three conditions, they are with the same protecting group, and here only difference is solvent, right? So these two reactions will give us the formation of different products due to change in temperature and the solvent, effect of temperature and the solvent in these two reactions. Here you can see that the product is formed 80% with Falkenhayn selectivity. So under these conditions, that is THF at 0 degree centigrade, there will be less gelation, that 80% of the product will be formed with Falkenhayn selectivity, whereas 20% of the product will be formed with anti-Falken selectivity. Whereas if we change the solvent from THF to DCM at minus 20 degree centigrade using the same Lewis acid, then 99% of the product formed will be with anti-Falken selectivity, and the product will be formed through chelation. Now, if we compare this example and this example, here the temperature is decreased further, but the Lewis acid used is here TiCl4, here magnesium bromide, but the product formed is again with 99% diastereoselectivity having anti-Falken selectivity, and the product is formed through chelation. Now, if this protecting group is changed to tertiary butyl dimethylsilane, we compare these two, temperature and solvent, they are same, and then we change the Lewis acid. The change of Lewis acid has led to the formation of product with 95% diastereoselectivity with Falkenhayn selectivity, or polar Falkenhayn product is formed, and the transition state involved is non-chelating transition state. So we can see that boron BF3 thread, this does not chelate, and this will provide the major product with Falkenhayn selectivity. So this is the effect of Lewis acid on these types of reactions. Similarly, the effect of temperatures, some of the effect of temperature we have seen in the previous slide in the two reactions also. But overall, if we are to generalize the effect of temperature, it has been found that lower the temperature, higher will be the formation of the product with anti-Falken selectivity. So that means higher will be the chelation. So lower the temperature, higher will be the chelation, and higher will be the diastereoselectivity of the product formed with anti-Falken selectivity. So this can be explained from this reaction. If we use 4R 4-diphenyl phosphoryl 2-methyl pent 1-ene 3-one, this is the substrate which is used to do reaction under these two different conditions. Here we are doing the sodium borohydride reduction. Solvent here is methanol, here is ethanol. And here, in addition to sodium borohydride, we are using cesium chloride also. And the temperature of the reaction is 20 degrees centigrade. Here it is minus 78 degrees centigrade. And as we lower the temperature from 20 to minus 78, we can see the favorable transition changes from non-chelating to chelating. And similarly, this transition state will lead to product with Falcon selectivity, whereas here this transition state will lead to the formation of product with anti-Falcon selectivity. So you can see the temperature affects the formation of products in these types of reactions, and lower the temperature, higher will be the formation of anti-Falcon product. Similarly, these are the two more examples of chelation leading to the formation of products with anti-Falcon selectivity. So when Grignard reduction of this ketone, alpha hydroxyketone, is done with phenyl magnesium bromide, we will get this as the major product with anti-Falcon selectivity. Similarly, in this reactant also, when phenyl magnesium bromide is reacted with this carbonyl system, then also reduction will lead to the formation of these types of hydroxy compounds with anti-Falcon selectivity, because the transition state involves chelation. And these are the references which have been used for preparing this lecture. Thank you very much.